Um, Everybody's still coming in, so I'm going to give it just a few more seconds. Let's wait for everybody to get settled in, take a seat, get comfortable. And there's a lot of people. We have a lot of people registered for this really fascinating, interesting webinar. And so we'll just give it some more time for everybody to really get in, and then everybody else will join us as we go. Let me just give it. I still see the count going up, so I'll just let it go a little bit. Hello. Okay, and I think we can start. So hello everyone, and welcome. My name is Davide Scher. I am the co-founder and CEO of Voxel Matters, a leading media and market research company dedicated to additive manufacturing. Since 2013, we've been tracking the evolution of AM technologies, reporting on daily developments. Since 2021, we've been publishing market studies from our proprietary databases, analyzing and forecasting AM industry trends in terms of materials, hardware, and services, mostly. Today, I'm really excited to host this session on one of the most important developments in metal additive manufacturing, the qualification of advanced superalloys for binder jet production. This webinar that we organized as Voxel Matters brings together experts from HP AM Solutions, Tecnalia, and Continuum Powders to discuss the technical journey of qualifying M247, a nickel-based superalloy for use on HP's metal jet binder jet platform. Together, we'll explore why this matters for industrial adoption, especially across segments such as aerospace, defense, medical, and energy, and what steps manufacturers can take today to prepare for the next wave of superalloy adoption in AM. Before we begin, a few service notes. On the right-hand side of your screen, you'll find the presentations and supporting materials made available by our panelists. We will be running surveys throughout the webinar, so please fill them out as they pop up, and we'll discuss the results together. Please feel free to submit your questions in the chat box that you also see on the right-hand side of your screen at any point. We'll address as many of the questions during the discussion and follow up afterward if needed. So, without further ado, let me quickly introduce to you our panel. We have with us Brett Harris, Senior Global Product Manager at HP AM Solutions, Rocio Munoz Moreno, Principal R&D Metals Technologies at HP AM Solutions, Dr. Inigo Agote Belocchi, Team Platform Manager, Manufacturing Processes and Materials at Tecnalia, and Kevin O'Shea, General Manager at Continuum Powders. So, let's get started. Our first speaker today is Brett Harris, Senior Global Product Manager at HP AM Solutions. Brett, welcome.
Hey, thank you, Davide.
Thank you. And go ahead.
No.
Yes, to kick us
off. I interrupted you, sir.
Fantastic. Can you tell us a little bit about HP AM Solutions material qualification framework and the expansion into high-performance superalloys, and basically the work that led HP to prioritize M247 for qualification?
Absolutely. I appreciate that, Davide. And good morning, good afternoon, everyone. And thank you, Davide, for the introduction. We're excited to have everyone join us today as HP, Continuum, and Tecnalia come together to share our technical journey in qualifying this nickel superalloy M247 for the HP metal jet printer. Kind of in the lead up to this webinar, I received a number of questions and kind of messages and all from industry peers, and most of them centered on three main themes. Why M247, for binder jetting, why Continuum Powders, and why Tecnalia. And so, as you'll see, in our journey in developing this alloy, we each bring core competencies to this development journey. HP knows how to print. We know how to layer powder. We know how to process control within the printer. Continuum knows how to tailor powder to the desired requirements that we needed for our system, the sustainability focus and powder production. And Tecnalia has deep experience with M247 and across a lot of industries, and their sintering expertise and the independent technical assessment, which we think is really important to this whole process. This collective core of competencies ensures a robust outcome for customers. So why M247LC? Well, as HP and Continuum began exploring various nickel alloys for the metal jet system, 247 quickly rose to the top of the list. Why? Because it's a very difficult alloy to weld, but it's widely used in aerospace and gas turbines, hot gas environments where high creep, fatigue strength, oxidation resistance, and microstructural stability are required at extreme temperatures. And almost all M247 applications are produced by casting or forging at this stage. The susceptibility it has to cracking, particularly when using laser-based processes, has really limited its use thus far in additive manufacturing modalities. And so consequently, the range of applications that can be produced are fairly limited. So we feel that this material, with its challenges in terms of being adopted in additive, lends itself very well for binder jetting and being able to expand the design breadth and the capability within those parts and those industries. I talked about why Continuum. Well, I don't want to steal Kevin's thunder because he'll talk about Continuum later, but one thing was clear: HP does not produce metal powders. We're not in the business of producing powders, but we know what powder characteristics and properties work well with our printers. And so Continuum's technical team worked with us to achieve the type of powder that's needed for our system, produce the powder for our process, and then more importantly, we wanted to ensure that process is repeatable and scalable. And so that, from terms, those check boxes were met with the Continuum team. And then their corporate emphasis on sustainable circular powder production really aligns with HP's corporate objective to empower customer sustainability. That's one of our core sustainability objectives as a corporation. And then lastly, why Tecnalia? Too often, and based on my past experiences, equipment OEMs will develop new materials in a vacuum, behind these closed doors, kind of keep everything to themselves and with very little input from outside their organization. Our approach is different, where the Tecnalia team enters the picture. The Tecnalia team brings deep experience, as I mentioned, with 247 and their sintering expertise, as well as and understanding what acceptable properties and the objective analysis required to really provide an independent feedback loop to provide confidence for the achieved outcomes. So we really value that independent view that they bring to the table. And so as you can see, with our open materials platform on the metal jet system and the materials qualification process that the rest of the team will kind of go over in a little bit more detail, we were providing customers with outcomes that really utilize the collective strengths of our trusted partners. So that's kind of a summary of what we're looking for and how we kind of approach the metal development or the powder development process here.
Fantastic. Thank you very much for that, Brett. I wanted to just remind everyone that we've shared the first poll. And I don't know if you're curious about the results, but the question was, what is the biggest factor in your alloy selection? And 44% said mechanical performance, strength, and ductility. Actually, that now went up to 47%. And 38% is qualification, certification, and certification requirements. And very far behind is corrosion aware resistance, cost and availability of powder, sustainability, and recycled content are further down. So those are the two top ones. We'll talk more about the polls later on in this session. So Thanks again, Brett. That was a very clear look at HP's qualification roadmap and processes. Let's now turn to Rocio and Inigo to dive deeper into the technical journey and current results. Rocio, go ahead.
Okay, thank you very much for the kind introduction, Davide, and thank you, Brett, for the very motivational introduction on the topic. So good afternoon, good morning to the audience. Today I'm excited to take through this journey that combines the innovative digital manufacturing together with advanced process engineering, and of course always looking for outstanding part quality and dimensional tolerances through additive manufacturing. And the truth is that as binder jets continues to gain traction on the industrial application, let's say, so we get more requests, and it is more evident that we need to go through the qualification of more materials, and in particular high performance materials as the one that we have on hands today, right? Fortunately, maybe we can go into the next slide if you want, or I can put it. Let me see. Yeah, so we have the experience at HP to be qualifying the stainless steels on our platform since the early beginnings of our technology foundations, let's say. And so this is the secret behind that we can trust and ensure, let's say, that this solid foundation is going to accelerate the development and validation of new materials, right? So basically our mission here together with other materials is to build a reliable and repeatable process to support the adoption and later going into mass production. And today I will be very glad to share how this journey is on the different stages that you can see on the slide. And if you have questions, of course, let me know and we'll go into the details. Basically, we can say that our journey starts on a risk assessment stage in which we focus on the compatibility of powder and binder. And here we need to ensure powder safety properties and, of course, verify the powder specs, the standard specs. And here it is about alloy composition, particle size distribution, and, of course, flowability in terms of apparent density and tap density. These are essential, fundamental, that we need to learn from the powder. And here, together with Continuum, we went into the details. But, of course, we also extend our understanding of the powder not only on the standard powder metrics, also with the extended R&D metrics that we have been learning through our investigation during the last years. Hopefully, at some point, those specs are candidates for being standardized, but here we have a lot of focus as well in other metrics as cohesive index from the avalanche test, or powder surface interaction on the infiltration with the binder, surface tension, etc. So basically, with all these metrics, we try to understand what is going to be the influence of the powder properties on the process performance and the final part quality. And to complement these properties, we also focus on the microstructure of green and sintered parts. In this first stage, I can say that we focus on a very important checkpoint, which is building up what we call an analog press part or a green press part that basically is a combination of a binder and a powder that we compress and later we sinter, which helps us to get an idea of how an analog part is going to behave, so avoiding the impact of the layered form structure. And so we characterize here the green density, the green flexural strength, and if we sinter, going through the sinterability, alloy composition, and density, etc. Here for the nickel-based superalloys in particular, it was very important to do this preliminary analysis in order to understand if we reach it to the good green flexural strength, and even more important about the alloy composition, as how, in the case of these nickel-based superalloys, the specification referring to the composition in terms of carbon and oxygen is pretty demanding, right? And we can say that we successfully passed it. So after this compatibility verification, we jump into what we call the process screening or the development. And here again, we take advantage and leverage our previous learnings with our previous materials qualification. And we jump directly in what we find the standard HP print mode. We start from here, and of course, in order to make efficient this approach, we always prioritize which are the properties we want to list down, right? Always considering cosmetic, density, mechanical properties, dimensionals, etc., but all targeted with the mission of looking for quality, robustness, and throughput. With this, we go through an iterative process through the development, and thank you to multiple layouts combining diagnostic parts with other application proxies. Parts together with multi-level functionalities, which allows us to work with different print modes on a single job, and also considering process monitoring as visual or thermal inspection, which also help us to close the loop and understand how to converge on that iterative qualification process. Most important here is to say that we confirm it with the M247LC, and here thanks as well with Continuum and Tecnalia, like very close collaboration and with a flowable, let's say, good communication, we managed to develop this print mode in less than 4 jobs. And so this is a very efficient way to get a process center, which helps streamline development and reduce cost, right? So once we get into the print mode, let's say the process center, we jump into the next stage, which is basically the validation, the repeatability, looking forward for a reliable process, let's say. And here we evaluate the print mode across multiple dimensions. And here you can imagine job to job, printer to printer, lot to lot, cycle to cycle, all along different layouts of the plots and different workflows. Again, here, I'm not going to repeat, and I know this is really well demonstrated, how we got the qualification on our stainless steel with dimensional tolerances, design for manufacturing, and the overall operation and equipment efficiencies. And here is when we are ready to later jump into the qualification requirements. And here is when we deliver the data sheets, with looking at the reference standards, as it can be ASTM, MPIF, and as we have demonstrated with our partners, as it can be with GKN, Indomem, AMES, etc. So basically, all in one is a very structured process that we have been putting together with Tecnalia and Continuum. We'll show now together with Tecnalia how it was in the case of the powders of the 247. But just to finish with this introductory description of the qualification, I want to explain that, let me see if I can, yeah. The secret recipe behind all this very thorough and deep technical, let's say, structured methodology to develop the qualification of a material is accelerated, and I can tell you that we can move fast and very smart way with, again, our quality, robustness, and throughput vectors always as the mission, thanks to the network. And here it is thanks to the HP Metaljet ecosystem network, where we pivot all our developments. And here I need to say thank you to Continuum and Tecnalia. I think the best team for developing this material now in Banderjet, and now to prove with the results that Inigo is going to show. Good.
Thank you. Let me just very quickly interrupt. I wanted to give you just a quick view of our second survey. It was about the alloys that our audience is using for AM, and the top answers are stainless steel and nickel-based superalloys. So titanium is very far behind, by the way, which is kind of surprising, but those are it. We'll talk more about this later. I just wanted to remind everyone to feel free to write questions in the chat box. We want this to be as interactive as possible, so we will answer them as we get them, or at the end in the Q&A session. So feel free to write your questions. And sorry about that. Inigo, go ahead.
Okay. Thanks, David. So just moving forward a bit more the webinar. So yeah, from Tecnalia. Tecnalia is a private research institute in the north of Spain, and we've been working with Banderjet already for many years. And in this powder qualification journey, we are contributing with the powder assessment itself, right? So if we want to have a powder that is adequate for the binder jetting process, we need to bear different aspects in mind. The first one, of course, we need to make a proper chemistry analysis of the powder, just to make sure that we have the nominal composition we are supposed to have, to avoid further problems, which in this particular powder are very important. For instance, the carbon and oxygen levels. Then we also need to have a look into the physical properties of the powder, meaning that particle size distribution, and then all different physical properties of the powder. We also take a look into the sintering activity of the powder, because we need to have a good balance between the flowing properties that we will also evaluate and the sintering activity of the powder. We need to have a good combination or a good balance between how good the powder can be deposited into the printer and the final sintering activity of the powder. So we also evaluate the sintering activity of the powder. And together with that, as I said before, the evaluation of the rheological properties, the static flowing properties, as well as the dynamic flowing properties. So with that, we can have a very good picture whether that powder is suitable for the binder jetting process. Of course, later on, we need to print it, then we need to sinter it, evaluate the mechanical properties, etc. But with that, at least we can have a first image of that. So just I'm going to present some results we got with this powder in particular. As I said before, I'm going to talk a bit more about the particle size distribution, the morphology of the powder, which I haven't really mentioned before, but we are going to present some scanning electron microscope images. We need to have a good powder, good flowing powder. That means normally having spherical particles, nice spheres. We're going to have a look at them later. And we are going to present a bit more as well the packing properties of the powder, as well as the flowing properties of the powder. So going to the particle size distribution, the powder that we got from Continuum shows quite monomodal particle size distribution, quite similar to the laser powder bed fusion powders. We compare that to the typical binder jetting process. In this particular case, we can say that we have a slightly coarser particle size compared to the typical particle size used in the binder jetting process. However, due to the liquid phase sintering of this material, as you will see later on, the densities we obtain with this powder are good, although the starting powder particle size perhaps is slightly coarser than the typical. As I said before, we have quite a monomodal distribution with very narrow also distribution of the powders, with D50 around 23 microns. Just to give an idea, the typical binder jetting powders are below this 20-25 microns. So that's, as I was saying before, this is a slightly coarser, but it's still good enough for the sintering process. And that's going to have a good impact in the flowing property compared to finer powders. So then that's a good combination, a good compromise for the process. We also evaluated the morphology of the powders using the scanning electron microscope. It is important to have, as I said before, spherical particles that certainly will help the flowing properties of the powder. We are looking for nice spheres with little satellites, no hollow particles. So here you can see images taken at different magnification, in which you can see that the sphericity of the powder is rather high, still some, if you want, elongated particles, but very few, and very few as well as satellites. We haven't seen hollow particles either, so that's a good point, and a very nice microstructure of the powder. I think I lost the presentation, David. I don't know. I touched something that I shouldn't.
I knew it was gonna come back up.
Sorry, it was me. This is live. Okay, so moving forward a bit, packing and flowing properties of the powder. Here you can see different data for the bulk or apparent density and the tap density. Those two parameters are very important if we want to have a high green density and controlled shrinkage during the sintering process. Here you can see that we have quite a nice tab density, around 65% of the theoretical density. That is a nice value, quite comparable to other typical binder jetting powders. And we also calculated here the Hausser ratio, which give us an idea of the flowing properties, the static flowing properties of the powder, which a value of 1.12, which is ranked in the good area of the flowing properties of the powder. So that is also a nice results and a good results for the later sintering and shrinkage of the powder. And the final slide about the powder characterization is the evaluation of the cohesive index. The CI stands for cohesive index, and that is an evaluation that was carried out into the rotating drum device. So basically, there you can see the different cohesive index as a function on the rotating speed of the drum. So you can see that we are always in the limits or in the area between the good and the fair. Again, saying that we have a good powder for spreading an uniform and good quality powder layers into the machine. So all in all, so far we've seen that this powder, despite being slightly coarser than the typical binder jetting powders, behaves pretty well. And I'm advancing a bit to what Rocío is going to say now, but the sintering properties of the powder are good despite the initial coarser particle size. I think that perhaps you can continue, Rocío, with the...
Thank you.
Yeah.
Thank you, Íñigo, and thank you for the introduction and the characterization of the powders. As I said at the beginning, right, first stage kind of accomplished. I need to add to here, we couldn't put all what we did, but basically we also did the press bars and we confirmed carbon and oxygen as Íñigo was introducing. And of course, once we got the compatibility check, we went into the next stage of development and screening. As I said, we started with the standard print mode, S100 for stainless steel. And with this powder, we predicted that we were going to have some kind of slight cosmetic issues to start because this powder was a bit coarser than what we used to work before. But we needed that, right, to have a starting point. And so to start prioritizing all of our properties, converging into the full, let's say, combination of all of them. So with this first standard print mode, we got the green properties okay in terms of green flexural strength, density, but we got a bit of crazing, what we call it is in the bottom side of the parts, we got some kind of sliding of the powder. So probably this was too dry. And so in the next job, we worked a bit on the recoater parameters and we improved the cosmetic to get it to perfect. So bottom and I mean the top and the bottom of the parts were completely okay, very sharp angles, and we confirmed here to reach into the 97% with the green density. I think it was, we'll have it in the next slide, but it was between into 50 to 53%. And with the next printed job in the third one, we went into a bit of change on the recoater, layer thickness, and the strategy on the passes. And we confirmed together with the Tecnalia team that just with the sintering at high vacuum, we went into results above the 98%. As I said at the beginning, and it is kind of nothing new because we did it before with our stainless steels and with our diagnostic parts plot layout that you have on the top of the figures. You can see, I think there were two levels in this kind of job. And so we could use multiple printing parameters in order to accelerate the design of experiments and be effective on the selection of the final parameters. And on the image below, you can see that we also combined proxy applications together with other process parameters as diagnostic parts that we'll be glad to share and show the final sinter parts when meeting probably in Fornex in the following weeks. So the next slide is basically the convergence, no, of our compatibility confirmation, development confirmation, and showing you the whole journey. Basically, it is not that you get everything on the first job. It is the third job that you got it. But getting results of this kind in terms of in the second sintering and in the third job trial above the 98%, we can say it is a good success. And so it is now that we are working together with the whole team here on the validation and the qualification through the datasheet by the following months, and we'll be glad to share more details in the upcoming weeks. And that's all from our side, I think, David.
Thank you very much. And before we go on to Kevin, just a quick preview of our latest poll about the audience experience with M247. And while more than 40% have used it marginally or have heard of this material, most of our audience, not 48%, said this is their first introduction to M247. So we'll talk more about this at the end of the session. So now let me introduce Kevin, who will discuss from Continuum side. He'll tell us about how these partnerships and how these we'll look at the supply chain and production side and how these partnerships and how the continuous production capabilities are enabling these results. Just check the mic, Kevin, please. Oh, there you go.
Yeah, thank you. Thank you, Federico, and thank you all for joining today. It's a great pleasure to be here to discuss both Continuum, but of course, the ecosystem generated with HP and Tecnalia around this unique alloy. For Continuum Powders, really our driving forces around three different areas. Number one, sustainability. Two, security of supply for customers as they advance into these application spaces. And lastly, powder quality and powder customization for these unique advanced manufacturing processes, specifically binder jet. Continuum is now scaling production of many alloys, and I'll go into that. But we'll talk about M247. You can see a rendering of our Greyhound system of atomization. It's quite unique to us. We design and manufacture them. One key point to note is the portability. In any chase of sustainability, we also have designed this system to be able to go where the powder is needed, but also more importantly, where our reclaim streams that we will tap into for full circular economy. As we grow and scale, that's also a key point to eliminate carbon reduction, eliminate carbon use or generation. And so excited to drive sustainability by also advancing the manufacturing of binder jetting and other systems. The company on those foundations around the sustainability, we do use reclaimed sources, and I think M247 low carbon is a fantastic example of an alloy today that's only casted. But we're driving our production off of reclaimed turbine blades, which may have not found a home to be recycled. And so that is core and nature of what we do, is to ensure a full circular economy. This has many advantages, of course, both the sustainability impact, but more importantly, a security of supply. And so we do feel is important, especially that customers do not have to find metal powders that go all the way back to a mining event. It is great that we can actually take alloys today, especially advanced alloys like M247, and put them back to work and make sure those very expensive elements don't have to come out of the earth right now. They can come from usage. Lastly is really around the quality and the customization of the powder. We are very amenable in our processes to define and work together with, as an example today, with HP and Tecnalia to ensure that the quality of the powder is designed for the unique applications. And I think binder jetting is definitely an area that has some unique properties to it that any powder off the shelf won't work. And that's true for other advanced manufacturing processes. So we not only strive to create a solid ecosystem of support with HP and Tecnalia and other types of manufacturers and research institutes, but we are open to really customizing our powders and giving the quality that's truly needed to get these parts manufactured. So it's bringing a holistic approach, and very excited today to be allowed to present our piece in that area and creating that ecosystem. Where we go next beyond the M247 is really a journey of new powders. And so we'd love input today on where to go next and what powders that HP and Tecnalia can deliver to other applications. The company is robustly manufactured over 35 different alloys, but for probably many on the phone, you have a realization that there's many more to come, and guidance from this team of members and other people in the industry will be fantastic for us to set out that roadmap and journey of what comes next. But MAR247 low carbon is actually a great bellwether, as Brett highlighted, fitting into many needs in the industry. It's binder jetting opens up the capability beyond casting. It's a fully recycled option today, significantly loosen carbon footprint, but more importantly, ensuring that the powder design meets HP's requirements on binder jetting, and then proven out with Tecnalia and their sintering capabilities. So excited to learn more on the questions, and happy to introduce Continuum and this wonderful ecosystem to bring this to the marketplace.
Thank you very much, Kevin, and thank you everyone for these great presentations that have actually sparked quite a bit of discussion and questions. A couple of them came in just before your presentation, Kevin, but we'll go through them now. In general, I guess I can try to pick somebody to answer a question based on what I think might be most appropriate, but feel free to jump in or and add anything you want to add. So I'll try to go in order. Let me go for the first question that came in, and it's as you look ahead, what do you see as the most impactful innovation that would quickly accelerate the qualification and industrial adoption of superalloys over the next 5 years? And really, I think this is a question for everyone. So I guess we can go in order, or if somebody wants to answer first, go ahead.
I mean, I can go ahead and take a initial stab at it.
Actually, go ahead.
Everybody's looking at me, I think. So there you go.
Yeah, I was looking at you.
You know, I think probably a couple of different areas in terms of impactful innovation. You know, the one thing that I'll kind of draw from based on the poll that was sent or that was put out there is in terms of people's familiarity with 247. I was surprised at how many respondents this is their first introduction to 247, and or have very limited use, if any, use with it. And so I think in terms of the innovation that's required for adoption or qualification within for nickel superalloys with binder jetting, I think the main innovation that's going to be required is getting that knowledge and that experience of that with that material out to the public, being able to do new geometries or new applications with the material that I guess historically is as I pointed out, mentioned earlier, typically this material and in some cases most nickel superalloys have either been casted or forged, and when you do that, it tends to the cost for democratizing that material is pretty high, because the high mix, low volume type applications are kind of priced out of the market, you know, because of the cost of doing molding and everything, molds and all that for the application makes it very difficult for those type of applications to be accepted or qualified. So I think being able to allow this material and putting the nickel superalloys into binder jetting and being able to binder jet applications, you know, not everybody needs 100% dense parts in their applications. So there's a lot of application space out there that this could help kind of bring down the TCO or the part cost to a level that allows some innovation and some new thoughts around the geometries and design freedoms. So I think in that regard, that would be one area. And I think the other area is, as we kind of go through, one thing I wanted to point out is, you know, we're achieving over 98% density on these parts, and that's just at sintering. You know, if you want to do some heat treating or or hipping of these parts, I mean, you can achieve higher density. So there's room to get for flexibility in terms of what you're looking at application-wise and space-wise. So I think that's just really getting the knowledge out there to customers that this is capable and available to them.
Thank you. If somebody wants to add something, otherwise I have a quick follow-up question. Do you think?
I'll
go
just,
ahead.
if you don't mind, yeah, I'll just add to Brett's comments. You know, I think one of the other areas for continued adoption is really, of course, it's creating more ecosystems like this, right? I think the important part of this right now with HB, Tecnalia, and Continuum is now customers can engage and get these parts. They don't have to do this activity alone, and they can explore the capabilities of MAR 247 low carbon in applications they never thought about, because now they know where to wear. But beyond the points that Brett made, they would just be locked to casting, right, which they may want to get into. But just to elevate the power of binder jetting, you know, there's many degrees of freedom in the prints to alter geometries and part size within the same print. And so now there's a whole gambit. You're not waiting months of cycle time to see a part and then test a part. Binder jetting in that application is really critical to really give engineers design flexibility in a very fast response. And I think that's really critical. And from Continuum, you know, our mission is to get these highly sustainable powders and generate even more ecosystems. And we're working hard to qualify MAR 247 in hipping applications, other binder jet systems, other types of additive manufacturing processes like cold spray. So we're going to try to ensure that there's a whole ecosystem of advanced manufacturing processes to allow a rapid adoption. That where properties of MAR 247 may have not been thought about for certain applications, but now they can be because the ecosystem exists to get the parts made.
Fantastic. And my question is really quick answer from both of you, actually. Do you think that binder jetting will accelerate, you know, due to the particular nature of the technology, will make it faster to adopt new materials than powder bed fusion in the past, you know, so far?
Yeah, I mean, I agree with that statement, and I think I probably would not have said that or had the same response probably maybe 2 years ago. But you know, to Rothio's point, and is earlier in that, over time, what we have really learned about the metal jet and the binder jetting process is we know characteristically what powders need to look like and work well in our system. And so that really is short cycling the development process, such that we really can kind of zero in on a what we would say as probably a high probability of success in terms of the powder characteristic that will be put in our printer. Now, with that, as she said, you go through the cycling process of say, well, you got to tweak some process parameters here and there to make sure you get kind of optimize that, which is what they showed in terms of what the Tecnalia team and all has done is we kind of zeroed in on that and got to over 98%. So I think that process will continue, but we've really short cycled the development cycle, knowing what a good powder would look like, needs to look like to be successful in our system.
Yeah, and
go ahead.
Maybe here, I mean, just, I mean, of course, all what Brett said, but adding as well, no, that in PBF and laser-based, basically, in many cases, you need an alloy design stage, no? So here with binder jet, we see the materials expansion much more agile, versatile, and let's say efficient, because we are defining which are the metrics specs that allows us to predict how it is going to be compatible with the system without not needing to be too much linked to the metallurgy behind, no? Because it is all sinter-based additive manufacturing. What I want to say with this is that binder jet can accommodate commercial alloys. The truth is that here it is another powder metallurgy that myself, I can say personally, is in the journey, no, of learning all the metrics that we need to capture to predict, and this is all about powder surface metrics and leveraging previous. But all in one, basically, binder jet has the ability to accommodate those alloys that are already on the market, and especially with the added value of taking the sinter-based mechanisms and enabling those non-weldable through PBF, and so being much faster and agile.
Thank you. I have next question is a more technical question. Maybe Dr. Inigo can answer it, but it's have you measured the green strength, and what is the typical value in MPa?
I can start answering that question, but probably that goes over Rocio's roof. Anyway, as far as I know, we haven't measured the green strength of those pads, have we? We are still on that.
Okay.
Typical, but having said that, typical green strength values that we get with HP platform around 5 megapascal of bending strength. Of course, that all depends later on the powder packing density, packing properties. I mean, the broader the particle size you have, the more packed the powder is, so the higher the green density is, as well as the amount of binder you put into your green parts. So then, but just as a rule of thumb, we can say that we would be around 5 megapascal of bending strength.
Yeah, I agree. And the preliminary test that we ran, I need to say that because it was on the development print modes, we were varying different binder saturations. Okay, so we are from I would say 3.6 to 4.5, something like this. And so now with the next validation and qualification stages, we'll get the final data here. But basically, the metrics for the question, the metric of green flexural strength is all about of how we can handle the part, if it is strengthened enough to not be eroded, and so the dimensional properties to be stable for later the sintering, and we can confirm that this has been the case. So we have not been feeling that the parts are easy to erode. So till the moment we find good flexural strength to our references, and the compatibility test we run as well with the press pass were confirming, so it should be okay.
Thank you. And because we're on the technical side of things now, I'm going to jump ahead to another question on the this one is on the final microstructure. Can you comment on that, on the final microstructure with perhaps a fine grain and randomized texture, which will surely differ from cast material, to provide some significant performance benefits, especially for fatigue? I read it because it was a little bit long, but I think.
Okay,
shall I, or you want to jump in for things? Up to you.
You can go ahead with our learnings, and actually I didn't read completely the question, but probably here the question is how it compares with conventional and also with PBF anisotropic behavior. And as a general comment, you can expect on binder jet always to have isotropic microstructure, not only in terms of the grains, also in terms of the texture, the crystallographic texture. So Inigo, you can share with us.
Well, first of all, again, as far as I know, we haven't finished the microstructure analysis. After the sintering process, we need to have, especially the final application is a high demanding application in aerospace, for example, we need to do a heaping process to fully close the porosity, and later we need to do a specific thermal treatment to obtain the very characteristics gamma prime microstructure that will give the material the good mechanical properties, especially high temperature. So having said that, and comparing that microstructure with LPBF, with LPBF or with any laser technology, there are many difficulties to get that material without any crack, but we wouldn't have in this particular case this columnar structure. And compared to the casting, we do have, because we've seen the other materials, smaller grain size compared to the casting. That potentially could increase the fatigue properties compared to the casting material. Again, that is not only ruled by the microstructure, but also by the interstitials, such as carbon and oxygen. So we need to have a look there as a whole. and evaluate the mechanical properties, taking into account the microstructure, carbon content, oxygen content, and the chemistry, overall chemistry of the material. So again, we are expecting to have a finer microstructure compared to the castings, and no columnar structure compared to other laser-based AM processes.
And to further follow up, was there sintering deformation? Have you tested for that?
So far, what we've done, and Rocío can jump on that, but there are quite simple parts. For sure, it's going to be deformation during sintering, depending on the part you manufacture. That is life. But there are different strategies to overcome those deformation and those defects in sintering, such as initial design, simulation of the sintering process, so you can compensate in green state your part, and also follow different sintering strategies with light setters or ceramic setters or other kind of materials. But I mean, that is one of the things of the sinter-based additive manufacturing processes, that the printing process can allow you to print many configurations, but then the sintering step need to be taken in very carefully to avoid any collapse of the part or deformation. So certainly we're going to have, depending on the part we're going to do, but I'm quite optimistic that we will be able to compensate and to accommodate any shrinkage to have the final part in good shape.
Thank you. And I'm sorry, did you want to add something?
Just a comment here. Somehow it comes here the beauty of the next stage, no, on the validation, working on the dimensional tolerances and the shrinkage factors, basically to later design the part that we are going to print, no, the exact design. So I think we are there.
Great, fantastic. And now there's a question about the material before printing. So Kevin, maybe you can answer this about. This is specifically about the potential explosion risk of these powders. Well, the question is about during the process, but also explosion risk before printing, such as for materials like titanium and aluminum, I guess. Is this the case? And if that's the case, has there? Did you do any characterization of these explosion risks?
Yeah, and I answered online as well. The general response is, yeah, this is nothing like titanium risk or aluminum risk. This would fall in the same categories as other nickel alloys, like a 718 or a 625. So explosion risk is not under consideration for these types of, as a EH&S consideration. Typical EH&S consideration would be around that these high nickel alloys contain some heavy metals, and so it's more about particle control and inhalation control because of concerns of maybe some other elements in the alloy, but explosion risk is not a concern for this alloy.
Okay. Well, and Davide, I'll add to that is Kevin can attest to, one of the first questions I asked him about this powder, about any of the powders that we ever put into our printer, is we need to look at the explosivity rating on it. And so that was one of the first hurdles that we cross over before we put anything in our printers. So.
Fantastic. And I think you already answered this one also, but I'm not sure if the entire audience has access. Is there a potential for higher density with HIP after sintering, I guess?
Yeah. It is probably the next step to publish, and we are confident that with this 98% and with the microstructure we are getting, we'll close the porosity further through the hot isostatic pressing, as it is expected for these high-performance nickel-based superalloys.
Yeah, and I would also just add, typically casting would have much less, would have more voiding and more voids available. So hipping is a hard requirement, but I think in applications of binder jetting with these types of sintered densities, that opens up application spaces that may not need hip, but hip will actually, yes, push it higher. So I think that availability of binder jetting allowing as sintered parts now can get access into application spaces.
Of course. And will you publish any mechanical property results, high temp, tensile fatigue and creep for binder jet of 247? If you have preliminary results, can you discuss it compared to the cast materials?
So I would say this is the plan. No? So this is
I would say the short
plan.
answer is yes. The plan is to publish data sheets on this as we finalize all the data gathering and the results. Our expectation is probably over the next 3 months is with metrology and doing all that work, it takes time to collect all that data, but we will, after Christmas, first of the year, we'll be in a position to have the data sheets readily available and that information to share.
Mm-hmm.
I think from a preliminary results standpoint, as the team has already mentioned, the first thing we really look at in this process is, can we get to a center density at or above 98%? We've hit that, kind of that checkbox and said yes. And so now that gives us a lot of confidence going forward that, the microstructure, the hipping, things of that nature will help close all those things down and have a nice outcome that we can share from a data set perspective.
And following up on that, what is the most critical process parameter for final part quality?
So
the final part
we can take a poll. We can take a poll on this.
Yeah, that's probably a good idea to do a poll on it. But Rosie, I'll let you kind of speak to that.
No, well, in this particular case that we started with the Voxel powder, we were touching more about the roller speeds and we touched a bit on the layer thickness, but it doesn't mean that it is the most critical one. This has been this case, okay, because we wanted to get into these properties. It is always a balance of the parameters. Once you get a coarser powder, you expect more, let's say, sensitivity of the bed to be perturbated with the binder. If you get a finer powder, you get more challenges in terms of the cohesiveness of the powder. So you need to understand it as a whole, let's say, integrated mechanism. And probably I'll have not a single answer for the process parameter, and it is a combination of all of them.
Fantastic. And this one I'm very curious. I'm also very curious about what is the production capacity for this alloy powder. If somebody wanted to use this for higher volume production, what is the powder manufacturing capacity that we are talking about?
Yeah, absolutely. So Continuum has just opened at the end of last year our state-of-the-art production facility in Houston, and so we are in the hundreds of tons capacity already available. But with plans to expand the ramp. So production capacity is not a concern for us right now for the future applications. And lastly, I think the other point that I noted, as we do grow in scale, Continuum is looking to now port these systems globally as well. And so we're primed as these applications get traction, like establishing footholds in Europe in the near future, and then potentially Asia as it expands.
Fantastic. And we are getting close to the end of our session. We do have a few more questions, but we'll get to them. Either I know some of them were answered online, and we'll get to the other ones. As a follow-up, everybody will. We got a lot of questions about whether you will get the materials. You can download them. You will get a recording. Everybody who registered for this webinar will get a recording of the session. So let me go through one more question, and then we can quickly look at the survey results. What is the sintering atmosphere employed, if you are allowed to reveal?
No, I was waiting for you. I think it was one of the slides that we presented before. It's a high vacuum atmosphere. It's around 10 - 5 millibar.
Okay. Fantastic. And just quickly, we can go over the poll. So why do you think, what do you think of the fact that about 45% of the audience this is their first introduction to M247. Is this an indication of the interest that there is for this material, or the fact that it wasn't, nothing like this was available yet? How do you view this? I guess we can start with
I'll touch on that real quickly. I mean, as I mentioned before, that to me is a good indication that the use of this material has got a very, I would say, kind of a narrow window in terms of use and the scope in which it's being used. So, these type of events, these webinars that allow the exposure of this material has got a lot of good uses, a lot of good capability in terms of applications, to be able to broaden that out. And then how binder jetting can help people do that. That's kind of the intent here, right? We want to kind of bring awareness of this to folks, and being able to use this, because like I said, casting, forging, those are really kind of the only modalities that can really produce parts right now with this material, without the cracking and all that's associated with it. And so we think this is going to be an opportunity for this material and this additive technology of binder jetting to be able to help broaden that scope.
Absolutely. About our other poll, I'm really surprised. I mean, two things I wanted to ask the panelists. One is that stainless steel remains the main material for additive manufacturing, and what do you think about that? And the other thing is that titanium, nickel is second, so almost up to steel for our audience, and titanium is actually a little bit farther behind. So if you have any thoughts on this order, I'll start with you, Kevin.
Well, I think it depends where the answer is coming from. So that order makes sense when you're thinking about binder jetting.
Okay.
Because titanium does not have a lot of profiles or access to titanium jetting for its material properties, etc. So yes, in the field of binder jetting, stainless steels and steels were number one, and now the transition is going into nickels, where tie is definitely being explored. So in the compass of binder jetting, yes. If you now flip that to laser-based systems, you're going to get a different order structure of what alloys are in use, where now titanium is probably number one, nickel's number two, and very little use of stainless steels and laser-based.
Okay, so we really are going a little bit over time, so I think we can close the session now, and I urge everyone to reach out for more questions to all our panelists. On behalf of Voxel Matters, I'd like to thank our speakers, Rocio Moreno, Brad Harris, Dr. Inigo Bellocchi, and Kevin O'Shea, for sharing their expertise, and thank all of you for joining us. If you in the audience are attending for next, be sure to connect with HP, Continuum and Tecnalia, and Voxel Matters. Feel free to reach out to make an appointment, or stop by the HP and Continuum booths indicated in the slide that you see on your screen. As an additional incentive, in case you need one, you'll find the M247 3D printed disc in the image there as a giveaway at both booths. So see the application, the materials, and the machines in person. This has been a really fascinating look at how superalloy qualification is unlocking the future of binder jet adoption. Please reach out directly at continuum.com/contact, or email at info@continuum.com for further details and collaboration opportunities. Thank you again, and we look forward to seeing you at 4 Next.
Thank you.
Thank you, everyone.
Bye-bye. Thank you.
Bye.